Hello, this is Monday, April 26, 2021. This is for both Aerospace Engineering Honors as well as AP Physics C. I want to talk about using Targeter within STK, within the Astrogator, of course, in STK. And specifically, I'm going to constrain myself to just Earth circular orbiting satellites. So far, you've learned how to do all these calculations manually. For example, if I give you the orbital period in units of seconds is what you have to work with, you would calculate the orbit radius by using t squared equals 4 times pi squared times r cubed divided by the universal gravitational constant g divided by the mass of the central body that you are orbiting, in this case, the Earth. Rearranging this equation and solving for the orbit radius would be the cube root of capital G times the mass of the central body times the square of the orbital period in units of seconds, all of that divided by 4 divided by pi squared. And this will give you the radius in units of meters. So if I give you the orbital period in, let's say, hours, you can calculate the orbital radius in meters from that, and then, of course, convert from meters to kilometers. Of course, using the same equation, if I give you the orbit radius, then you could solve for the orbital period if you need it, using the very same equation. T squared equals 4 pi squared r cubed divided by g divided by m. In this case, after taking the square root of both sides, t would be equal to 2 times pi times the square root of r cubed over g over m. And this is great. So if I give you a problem where you have the orbit radius, you can calculate and display the orbit. If I give you the orbit radius, you can calculate and display the period. Of course, if I give you an altitude, let's say h, then to get the orbit radius from that, r would be equal to the radius of the central body, in this case the Earth, plus the altitude above the surface of the Earth. So doing a little diagram, capital R is the radius of the planet, h is the altitude above the surface of the planet, and little r, the orbit radius, is equal to the radius of the planet plus the altitude above the planet, h. Great. And in STK, I can show you in a couple of minutes, if I give you t, you can just enter the orbit. And if I give you h, you can enter the orbit. And if I give you r, you can just enter the orbit, because these are allowable input parameters to define an orbit in STK. I recently gave a homework problem. It's called Homework Assignment 7, Problem Number 2, where I didn't give you any of these three parameters. Instead, I gave you the orbital speed, v. And the challenge was, okay, so if I give you the speed, how do you determine the orbit? Well, the formula is v orbital speed squared is equal to capital G, the universal gravitational constant, times the mass of the central body, divided by r, the orbit radius. So if I give you the speed, you can rearrange this equation and say orbit radius r is equal to universal gravitational constant g times the mass of the central body divided by the velocity squared. Okay, so what if you don't want to do even this much work? What if you would like STK to calculate the orbit radius for you if you're given an orbital speed v. Okay, so I'm going to demonstrate each one of these four possibilities for a homework problem for a circular orbit. So let's say I give you an orbital period of, let's just make it 8.30 hours. How do you calculate a circular orbit from that? What if instead I gave you an orbit radius of 8,300 kilometers? How do you put that into STK as an orbit? What if I told you that I have an altitude of, you guessed it, 830 kilometers? How would you put that into STK? And finally, what if I told you that my orbital speed was, I don't want to make it horribly slow, but I could, the moon is going 1,000 meters per second. So if I make this 830 meters per second, the orbit will be farther out than the moon's orbit. If I make it 10 times higher, 8.30 kilometers per, good question, kilometers per second, it will be below the surface of the Earth. So here I need to make up some number. How about 3,800 meters per second? Or if you like, 3.80 kilometers per second. And in each case, STK is going to generate the orbit for you. And of course, any one of these four inputs would be perhaps how I would start off a Hoffman transfer problem. And then, of course, you would need a second input of some sort and let SDK do the calculations to do the delta V1, delta V2, time of flight, all of that good information, all of that within Astrogator. So I suppose I should, I'm not going to worry about doing that part of it. So it is left as an exercise to the interested student to generate the second circular orbit and then use the Astrogator with the targeter function to calculate the delta V1 and delta V2 and the total delta V and the time of flight to do a Hoffman transfer from any initial orbit to a given second circular final orbit. Okay, so switching to the camera that just shows what I'm doing in SDK, I've launched SDK, I'm creating a scenario, I'm calling it Astrogator Targeter. It is asking me what objects do I want to insert. I'm just going to choose for now to insert a single satellite, and I don't care, we'll call it insert the default satellite and let it close. Okay, so by now you should be an expert with using STK to do some basic orbital mechanics. If I set this default satellite somewhere, it'd be nice to see it playing. Let's see what it did. So I'm going to just start off with a satellite at its default value. So I'm double clicking on a satellite that brings up its object properties window. And I see I don't want it to be inclined because that's too confusing for all of us. I'm just a little curious. Its altitude is just 300 kilometers above the Earth. I apply it, okay, and it should show up. There it is. Very tight orbit around the Earth. Nice. what I'm going to do is now demonstrate using the Astrogator to get things going. So back to the satellite. I'm double clicking on it to bring up its object properties window. Under Basic Orbit tab, I'm going to change the propagator from two-body to Astrogator. When you do that, it ignores whatever previous parameters had been set for that satellite. You have to start all over again. In the first case, I said, suppose I gave you the orbital period of the satellite. Well, then clicking on the mission control sequence window, selecting the first segment, I would suggest changing the coordinate type to Keplerian and changing the orbit element type to period. Finally, change the units to hours and select this input window and type in whatever value I gave you, such as 8.30 hours. The eccentricity really is 0. This is just the round off error in a digital machine. For our comfort level, and maybe to make the machine even more comfortable, you could set that to 0. I want all of our orbits to just be simple equatorial for the foreseeable future. So we're going to change the inclination from the default value for Kennedy Space Center in Florida to an equatorial orbit with an inclination of 0. For the propagate statements, I'm going to keep things simple. So I'm going to change the propagator from the Earth High Precision Orbit Propagator default version 10.0 to just Earth point mass. Now, this will make it run for 12 hours, which means it'll orbit the Earth many times. That's fine. It doesn't actually matter in this situation. And if I press run entire mission control sequence, I'm done with creating this first circular orbit. I had to zoom out a little bit, but there you can see it. And if you took the trouble to study it, it would orbit the Earth in 8.30 hours. I could slightly speed up the animation. You could watch the Earth. You can see that it's spinning faster than the Earth is around the Earth's axis. Okay, so nice. There's the first situation. So if I give you a satellite orbit in hours, when you click on this initial state, if you choose the element type now from period to, let's say, semi-major axis, it'll show you the value that goes with it, 20,812 kilometers. If you change it to apoapsis altitude, it'll show you the altitude above the mean radius of the Earth. In this case, 14,433.8 kilometers. So that's as simple as it is to input an orbit given its orbital period and let STK go from there. The second case I told you was, what if I gave you the orbit radius? And in that case, same story here. Under initial state, element type, instead of setting it to period, now set the element type to semi-major axis. Change the value to match whatever I give you. In this example, 8,300 kilometers. If it makes you happy, verify that the eccentricity is really 0. Nothing will happen when you hit the apply button. Apply really works for elements outside of Astrogator. To have the situation updated to this new input, you have to run the mission control sequence, this green arrow to the right. After you run it, this window will update. Ta-da! There's the new updated window. So if I zoom in, I will, this is a satellite that is in a much faster orbit around the Earth because it's much closer to the Earth. Now I have to kind of slow the animation down so that the satellite isn't speeding too fast for you to watch. If I simply change the element type to period and change the units over here to, let's say, minutes, it shows that in this example, that satellite has a period of 125.423 minutes. If I were to change the eccentricity to the apoapsis altitude, it shows that this circular orbit satellite is at an altitude of 1,921.86 kilometers above the mean surface of the Earth. So there's the second situation, done pretty well. In the third situation, I told you, what if I give you the altitude of the satellite above the Earth? So again, selecting the initial state in the mission control sequence, the initial state segment. This one should be easy to figure out. You want to change the periapsis. You want to change the apoapsis altitude, let's say, to the periapsis altitude. While you're at it, watch what happens. So if I change this value to what I suggested was 830 kilometers, when I changed to the apoapsis altitude, notice that it did not change. So right now, if I were to run this, it would end up being an elliptical orbit, which I can show you. I think you can recognize that as an elliptical orbit. Periapsis around here, apoapsis around there someplace. So you need to be careful that you change both the periapsis and the apoapsis altitude to whatever value I give you. If you just do periapsis altitude and let's say you do apoapsis altitude and you do eccentricity, you need to be careful that it accepts the current value that you're putting in and not a value from a previous situation. But here it is, run the green arrow, and now we have our circular orbit. There's its altitude. If you want to know what its orbit radius is, from the drop-down menu, semi-major axis shows that the orbit radius is 7,208.14 kilometers. If you want to know what its period is, again from the drop-down, you can change the units to minutes, and it shows it's 101.507 minutes. So I've just shown you how to very easily input satellites with 3 different givens into STK and let it take care of everything from there. The first given was the period in units of hours. The second given was the semi-major axis or the orbit radius in kilometers. And the third given was the altitude in kilometers. And by the way, you can change the units. They have quite a variety. And if you don't see what you need, you can customize it. And now for the fourth case. This one is not in STK by default as anything that you could just pick from a drop-down menu. This fourth case was, what if I gave you the orbital speed? Now, this is where the power of Targeter can come to work for you. So the way you could do this is in the mission control sequence, right-click on the initial state and insert before. From this window of instructions, select the target sequence. Right now, the target sequence doesn't have anything. You need to select the initial state segment and drag it, because you can drag it up and down, drag it so that it is embedded within this target sequence. And so what's going on here is you are telling STK, look, I'm going to give you a result that I want. I'm going to tell you what control you can modify, adjust, and you're going to go do what it takes to solve for me. Okay, so in this situation, you see these little bullseyes here. They are telling us what parameters we're going to allow STK to adjust. Which one will be the independent variable? Well, you might remember the formula that I had shown. When you are given orbital speed, you solve for orbit radius. So we're going to tell it that the variable that it can manipulate in trial and error is the semi-major axis. To do that, you put a check mark in that target icon. This tells STK of all the choices of what you can modify the radius of the orbit. That's the one thing we're allowing STK to change. You can have multiple variables for the problems that you're working on, but I'm just demonstrating how to use STK to solve this one homework problem. Now, what results do we want? Interesting, you should ask. There is a button labeled Results down here at the bottom of the Mission Control Sequence window. When you click on it, it brings up a whole large listing of folders of possibilities. There might be a better way of doing this, but I'm choosing to use the Cartesian elements as my route to solving this problem. There is a Cartesian coordinate system, and if I were good, I could turn it on in the 3D window. You would see that the positive x-axis, well, first of all, the origin is in the center of the Earth. The positive x-axis goes out to the Earth's equator towards the vernal equinox. That is the location in space where the center of the sun's disk is crossing the Earth's equator going from south to north. That is the positive x-axis. The positive z-axis is straight up through the north pole of the Earth. So we're really looking down from the positive z direction right now onto the north pole of planet Earth. The positive y-axis is chosen to be orthogonal to the first two directions and be designated by the right-hand rule, meaning if you point the fingers of your right hand from the center of the Earth towards the vernal equinox, close the fingers of your right hand by 90 degrees, that will point them towards the positive y-axis along Earth's equator, while your thumb points along the positive z-axis. I should have prefixed this a little bit more and have you ponder. So if I have a satellite that is at the moment that it is crossing the positive x-axis, in what direction is its velocity at that moment? The answer is moving towards the positive y direction. A quarter of an orbit later, just as that satellite is crossing the positive y-axis, in what direction is it moving? The answer, it's moving in the negative x direction. Another quarter of the orbit later, as the satellite is crossing the negative y-axis, in what direction is the satellite moving? The answer, it's moving in the negative y direction. So it's crossing the negative x-axis and it's moving in the negative y direction. And a quarter of an orbit later, as the satellite is just crossing the negative y-axis, in what direction is the satellite moving? The answer, it's moving in the positive x direction. So I'm going to dictate to STK, I want you to create an orbit radius at the moment that it is crossing the positive x-axis. And so that means the direction of motion will be in the positive y direction. So out of these list of 6 choices under Cartesian elements, I'm going to select the positive velocity in the y direction, or the velocity in the y direction, v sub y. This arrow inserts this component. Here's some details which you should sometimes care about and read. You can duplicate any of these components and then customize them for your particular application, but we're happy that this is with the Earth as its coordinate system. Everything else is good for us for today. So, okay, that is the only result that we care about. We don't care about the orbit period. We don't care about anything more complicated. We now have one independent variable and one dependent variable. Now click on the target sequence. This is named the differential corrector. Kind of a math term. It means the calculator of STK is going to find this answer using trial and error, but intelligent trial and error, somewhat mathematically advanced trial and error. Simple trial and error is called a binary search. So if I told you I'm thinking of some number between 1 and 100, and all I can tell you is you hit it, or you're high, or you're low, then your first guess should be halfway between 1 and 100, let's say 50. And if I tell you, oh, that's too high, then you know the answer is between 1 and 50. And you guess halfway between them, 25. And then halfway between the two ends where you know it's in between. That is a simple binary search. A slightly more sophisticated search, if you have an equation of motion, would be to look at the first derivative of the rate of change and use that and test it to see if you're high or low and go from there. And STK uses more advanced differential corrector than that. All right, so double click on the differential corrector. It opens up a dialog window about the corrector. The top part is all about your choice of the independent variable. Put a check in the box that says, yes, use the semi-major axis as your independent variable. From the last problem that I had put in there, its current value is 7,208.14 kilometers. That's the green orbit that you see here. That will go in as its initial value. In the maximum step size, we're telling it, look, we know you're going to be searching by sophisticated trial and error. We don't want you to wander too far off at a time. Don't take steps that are too huge, because you might overstep it and end up in some other region of solution space. In other words, there might not be an absolute minimum to some function. It might be a relative minimum, and you might end up in some other region of solution space. So this is something you would care about when you do more sophisticated analysis than this exercise today. The bottom half of this dialog is about the results that you want. What results do you want to use? We've only listed one choice. Put a check mark in it saying, yeah, we're going to use this as our results. Right now, the desired value is set to 0 kilometers per second, which would be infinitely far away from the Earth. I made up a value for this exercise of 3.80 kilometers per second. So that's where you type it in under desired value. The tolerance box here, you might want to pay some attention to. It's asking you, when can I quit searching for the answer? How close is good enough for you? And right now, the tolerance is listed at 0.0001 kilometers per second. That is 1/10 of a meter per second. That is extremely precise, right? So you could make this tolerance less, particularly when you're first searching for a solution. You might let it be, oh, let's say, be happy if it's within a kilometer per second. And then run it again and tighten up the tolerance once you're happy that you're in the right local region of solution space. The other thing I want to point out to you is there's a tab up here. And by the way, I'm going to just leave this at 0.0001 kilometers per second. There's a tab up here called convergence. When you really do analysis, you might check this one out. It says it will run this analysis 50 times, each time learning from its previous mistakes, trying to converge towards a solution. 50 is a good number for us to start off with. If you're doing a very sophisticated analysis with multiple variables, you might want to knock this down to maybe 30. You'll get a feel for it as you do things. All right, so we've set up our differential corrector. The next step, I mean, if I just hit the green arrow right now, surprise, surprise, nothing's going to happen. I just ran it, nothing happened. In order for SDK to take over and now actually solve, you have to change the action from run nominal sequence, drop down menu. You could choose to run the active profile just once so you can kind of see how it's starting off. But in this case, we're going to just follow the tutorial that they have online and say run the active profiles. So it can iterate up to 50 times trying to solve this problem for you. And green arrow to the right. Off it goes. And what you can see is it only ran once for some reason that I goofed on. I'm guessing I forgot to set the inclination to 0. Huh. So there's that dialog window explaining what happened. And I don't quite know what I did wrong. I'm going to run it one more time. Should get exactly the same result. Yeah. Okay. I'm going to pause this recording until I figure out what I've done wrong this time. All right, that was fast. I didn't even need to bother pausing it. I can see maybe here, maybe not, that these are the same number. That's good. 0, 0, 0, 0. That's all good. This is probably correct. And so actually, I haven't figured out what I did wrong yet. Oh well. Drats. I think what I will have to do is actually change my configuration here. So I'm going to make a change. On the initial state, instead of leaving it as Keplerian, I'm going to flip it over to express it as Cartesian. And in Cartesian coordinates, this is a component of the orbit along the positive x-axis, and I'm going to select that as my independent variable. Here is the y component 0, z component 0. So it's an equatorial orbit, and it's at this instant of creation, it's along only the positive x-axis. The y component of the velocity is 0. The initial value of the y component of the velocity. Did I say y here? This is x. Y component of velocity is at 7.43631 kilometers per second. Z component currently 0. And I think maybe I should check my differential corrector and say, instead of doing this in Keplerian space, let's do this in Cartesian coordinates instead. So I'm going to change the use to Cartesian. I'm going to deselect using Keplerian. And this still looks fine. Here's my target value. Here's my current value. I think this might work okay now. So let's run the sequence. And no, it still didn't work correctly. All right, this time I'm going to pause it again. All right, after pausing for probably a good half hour or so, I think I figured out what I need to do. So I've closed out SDK, I've relaunched it, tried it a couple times. Maybe we'll get it correct this time. I'm going to insert a default satellite and then close out SDK. You can see by the numbering, it's the third satellite I'm doing today. Close this out. I'm going to close out the time window so we have more territory. Shift this over, make this larger, hide this, double click on the satellite, change it to the Astrogator propagator. Right click on the initial state, insert before, target sequence, OK. Click and drag the initial state to go within the target sequence. And I don't need to do this, but I could choose to put the propagate inside the target sequence as well so that I can show you visually what it looks like. It's pretty cool. I'm going to change the propagator uh, for the propagator to Earth point mass. I don't think it matters whether I select initial state or propagate, but I'll just select initial state and select the results, again from Cartesian elements, select the y component, the velocity, as my results variable. And now I need to pay much more attention than I did before. So the initial state shows I'm starting at a 300-kilometer altitude, which is 6678.14 kilometers on the positive x-axis, but I have a non-zero z component because this thing is inclined probably 28.5 degrees. So I need to set that z component to 0 or it's never going to be able to find a solution. In fact, I'm going to switch coordinate systems to Keplerian and see, this is a little troubling for me. It says the eccentricity is 0.22. I want to force that to be 0. It says the semi-major axis is inside the Earth. That's a little scary and crazy. I'm going to make it at least above the Earth. Let's make it 7,435 kilometers. I'm going and it switched the other two variables here to values of 0. Again, this is 0, but I'm going to type in 0 anyways. So that's showing things in Keplerian. Now I'm going to switch to the mixed spherical coordinate system. And I see here, I'm okay with this. It says my altitude is like 1,000 kilometers. I'm horizontal flight path angle of 0 degrees, going in the positive y direction with this much magnitude. I'm going to see what it looks like in spherical coordinates. Not too bad, maybe. And I'm going to go back to Keplerian for a moment, and I'm going to see if I can make the apoapsis altitude just maybe 500 kilometers. So I'm editing that just so that I can show you better what things look like when this thing does do its job. And because I've made a change here, setting it to 500.5 kilometers, I want to see if I put that into Cartesian. Okay, this looks like it understands that. So hopefully I now have my initial state correctly set. I need to show which component I can change. I'm going to try doing this in Keplerian format with the semi-major axis as my only independent variable. Everything still looks okay. Clicking on the target sequence. Opening the profiles, which is the same thing as double clicking on differential corrector. Opening the profiles. I'm going to choose to use the initial state Keplerian semi-major axis as my control variable. I'm going to use the y component of the velocity vector as my x variable. And I'm going to uh, set it to that value I wanted, the 3.80 kilometers per second. I'm leaving everything else the same, convergence of 50 and so forth. Now, before I run the sequence, I'm going to run the sequence as the nominal sequence so you can see what the current satellite location is. And I'm going to try to adjust this window a bit and get it a bit more out of your way so that you can see the 3D window better. It's equatorial orbit, nice. It's 500.5 kilometers above the Earth, nice. Now, what I'm going to choose to do is change the target sequencer action to run active profiles. And finally, this one should work correctly. And what it will do, because the propagate statement is within the target sequence, every time that it tries a new value, it will draw the orbit that goes with it as it searches for its solution. So watch. Ooh, ah. And it shows after 22 attempts, it converged to a solution. It met the constraint to within a tenth of a meter per second. And you can see each orbit that it attempted. It was constrained to not change the R value by more than 1,000 kilometers at a step. So it changed, and you can see at the end, it said, oh, I'm pretty close. It didn't change it by a full 1,000 kilometers. Now, if I were to run this again right now, it would just do this again. Well, this time it's saying, hey, I started from there. So if I foolishly just said, now run nominal sequence, sadly, it'll go back to the original orbit because I didn't tell it to accept the results that it found. So doing this another time, I'm changing my action to running the active profiles. You can see it's searching for its solution. Whoop, it knows right where to find it. There it is. Now, to make it stay, you need to apply the results, and that's what this is. So apply the results, and now when I switch the action to run nominal sequence, it says, oh, these are the results I'm supposed to be using. No need to go searching for it. There is my orbit that satisfies this problem. Okay, so that was painfully long on my part, but this is how you can use STK to solve for an orbit radius, an orbital period, if the only thing given to you is that it's a circular orbit around the Earth with a velocity given. Now, if you want to see what the orbit radius is, I suggest that you click on the last segment, which is the propagate statement, and bring up the summary report. And in this summary report, you'll see all the information that you could possibly want to see, particularly when you go to the end segment here. It says, oh, okay, for example, the period was 12.677 hours, 779 hours. What else do you want to know? The altitude was 21,225 kilometers. The on and on and on. The mean motion, the magnitude of the velocity, 3.80, the apoapsis velocity, the periapsis velocity, because the eccentricity is 0, of course, they had the same. Here's the semi-major axis, inclination, right ascension, true anomaly at the end of this, true anomaly at the end of this. All this information, I feel I have successfully shared with you one thing today.